filters from the CAD model. And so there's things that I never talked about the filter design because I didn't have good images to make it easy to talk about it. And so I added a whole bunch more images today, and we will spend more than today wrapping up filtration because there's so much more to talk about. And we'll continue the same path of splitting our time between lecture and gather. So the first thing is I added, oh, don't tell me this won't work. Okay. I wanted to just show a fluidized bed. Let's see if this works. Here we go. Okay, there aren't a whole lot of great images of fluidized beds, although maybe the number is slowly growing as we get more people taking YouTube videos of many things. But wasn't that amazing? They put water up through that bed of sand, and now all of a sudden, it's a very different thing. So that's one fluidized bed, and then here's one more. This one is even more fun, courtesy of YouTube. So this is a bed of sand that is fluidized with air. And if you've never seen this with your eyes or felt it with your fingers, you're like, what is going on here? And what happens in a fluidized bed is the fluid pressure pushing up on the bed from the bottom exactly matches the weight of the media, the sand, per unit area. So that the pressure pushing up exactly matches the weight divided by the area, which is a pressure pushing down. And so each sand grain, or whatever the media is just kind of like hanging out there in what the sand grain experiences as being in perpetual free fall. It's at its terminal velocity because the fluid is coming up fast enough to hold it there. And so you get this very different material that acts like a fluid instead of like a solid. And you can move your hands through it easily. The video that I showed also has a clip of Mark Rober, the YouTuber, sitting on top of his spa filled with sand, and then they turn on the aeration system so that it fluidizes, and he just sinks into the sand when it fluidizes. So that's what we're doing inside filters when we backwash them. We are fluidizing the sand, and then the sand grains are moving around, and the flocks that were caught in the pores of the sand grains are knocked off, released. And so we end up getting a clean filter again, and we can start the process over. So today, now that we've seen fluidized beds, I want to go over some concepts that are important for understanding how filters work, ranging from porosity, sand size, the head loss, how much pressure drop there is as a fluid moves through porous media, and how much fluid do you have to push up through a sand bed in order to fluidize it. So we'll do the math for that, and you can actually. What's lovely is it's a relatively straightforward calculation to get a very good estimate of that. And then we may or may not get to this today, but there's then this big question about, well, what was the problem that Agua Clara was trying to solve when we invented the stacked rapid sand filter? And it's about the backwash dilemma of how in the world do you backwash a filter if you don't have access to electricity? And so that was what drove our design process. The first, porosity. So porosity is pretty simple. It's the volume of the voids that are created by the sand grains divided by the total volume. So volume of voids over total volume. And so as a little example, if you've got a cubic meter of dry sand, dry aquifer material, and you weigh that, and it ends up weighing 1,600 kilograms. So you got a cubic meter, it weighs 1,600 kilograms. And then you have it in a tank, and you put water in until it's completely saturated with water. And you weigh it again, and now it weighs 2,000 kilograms. So the first question is, what's the porosity of the aquifer material? What fraction of the aquifer material was actually voids, where there was air? And conveniently, we can just forget about the mass or the density of air. It's close to zero relative to water, so we can ignore that. And what we did is we went from 1,600 kilograms of aquifer material to 2,000 kilograms total. That means there's 400 kilograms of water in the pores. And 1,000 kilograms of water in a meter cubed would be, that's the density of water, right? 1,000 kilograms per meter cubed. So 400 kilograms out of 1,000 kilograms total is the ratio of the void volume. So the void volume, or the porosity, is 40%. Does that make sense? If we had filled that whole container up with water at a cubic meter, it would have been exactly 1,000 kilograms. We were able to put 400 kilograms worth of water in there. So it's 400 over 1,000. It's 0.4 is the porosity. And by the way, that's kind of the standard accepted porosity. It varies a little bit, but if you have a well-graded material of uniform size, that's roughly what the porosity is. What about the bulk density of the aquifer material? So this word bulk just means that it's kind of like the density that you get when you dump a load of it there. You know, you have your dump truck and you dump a load of it, and that bulk density is your dump truck held, I don't know, 10 cubic yards, and this was how much it weighed. If you take that weight in kilograms and divide it by a volume in cubic meters, that's the bulk density. So the bulk density includes the fact that material had some voids, and you're counting those voids as volume of the material. So the bulk density of this aquifer material, it weighed 1,600 kilograms, and it occupied a cubic meter. And so its bulk density is 1,600 kilograms per cubic meter. That one's easy. Bulk just means the whole thing, including the pores. And then, but we're also often very interested in what's the actual density of the aquifer material. So if it's sand, what's the actual density of the sand when we don't include the pores? And so this is a little more complicated. We have to figure out first, how much sand was there? Anybody know how many cubic meters of sand we actually had? We had 1 cubic meter of pores plus sand. We had 0.4 cubic meters of pores. So we have 0.6 cubic meters of sand. And we also know how much those 0.6 cubic meters of sand massed, what their weight was. It was 1,600 kilograms. So if we take those 1,600 kilograms and divide it by 0.6, the actual real volume of the sand grains, we get 2,700 kilograms per cubic meter. And by the way, I, of course, set this up so that it made some sense. The actual density of silica sand is around 2,650 kilograms per meter cubed. So that's what I was talking about here with this aquifer material, was mostly like quartz sand, or silica sand. Next question. Which of these materials will have the greatest porosity? 1 micrometer diameter clay, 0.2 millimeter diameter sand, or 1 centimeter diameter gravel. And to make this as simple as possible, you can just pretend for a little bit that each of these is spherical. So we've got spherical clay plates. They're not plates anymore. They're little spheres, a micrometer in diameter. Same with sand and gravel. Which of those has the greatest porosity? And goodness, Patrick, if there's any chance you can do an A, B, or C poll. Clay, sand, or gravel? Which of these has the greatest porosity?
Monroe, I have a question.
Yeah.
You're talking about like a meter cubed of each of those, right? Individually?
Yes.
Like, oh,
Yes.
like,
No mixing.
Okay.
And let's just give this like another 10 seconds, vote quickly, and then come back. Last chance for voting. Okay, so look, there's a bifurcation. Some people like clay, more people like gravel. For some reason, sand was not the favorite of hardly anyone. Did anyone wish there was another possible answer? Oh, yes, I'd love to know what Katie was thinking.
I feel like they should all have the same porosity if they're all like if it's 1 meter cubed of the same thing.
Katie, you win. This was a really badly posed question, but I do it on purpose because it's so easy to think that one of these has the highest porosity. If they're spheres, they're all the same. So Katie, thank you. That was excellent. So for those of you who voted for gravel, I think it's very easy to confuse porosity and another idea, which is hydraulic conductivity, or how easy is it to push water through this? So if I had asked you, which one of these is it easier to push water through? Then the answer is clearly gravel. But the void volume could actually be almost the same for all three of these. The void fraction could be almost the same for all three of these. Okay, but there's some fun results of this. If you were given some of each of these materials, how could you make something that had really low porosity? And we're not going to bother going through all the math to figure out exactly how you would do this. But can you think about like, how would you mix these three materials together to get something that in the end has a much lower pore volume? Anyone jump in with how you might play a game with these three materials and reduce the overall porosity?
I guess you'd want to fill in the gaps between each of the types of material. So if you had gravel like touching each other, there's going to be that small gap in between the pieces around it. So you want to fill that with the sand, and then you can fill that with the clay after to fit those smaller particle gaps. So
that's well said. Perfect, Ravi. And so now when you go to the farmer's market in the summer and you want to buy strawberries, and strawberries are sold by volume, you buy them by the pint. Should you look for strawberries that are all the same size in the container, or strawberries that are lots of different sizes?
different sizes.
Yeah, you can play the game. You can, if you get different sizes, you will actually get a greater mass of strawberries. Okay, any questions about that? Who would have ever thought that porosity could be fun? All right. Okay, maybe it wasn't. I thought it was fun. All right. Just one quick slide. In filter terminology, we have this effective size, which we often abbreviate as ES. It's a sieve size that 10% by mass of the sand passes through. So it's kind of a smaller dimension, smaller size measurement of the sand. And then there's a D60. Why they didn't call effective, why they didn't call effective size, always just call that one D10. And then D60 is the size, the sieve size that retains 60% by mass of the sand. And that's the size that we will tend to use, like if we're calculating head loss through a filter bed, a clean filter bed, we would use the D60 size in those equations. And then there's a uniformity coefficient, which is you divide those two. And what you would like is you're dividing the sieve sizes. And what you would like is for those two sieve sizes to be close to the same, meaning that you have sand grains that are pretty uniform in size. So a uniformity coefficient of 1 would mean that the same sieve that holds 60% of it also holds 10% of it, which isn't quite possible, but it's like they're really, really close to the same size. So and see, this connects back with porosity, right? If you have a very uniform sand size in your filter, it's gonna have a higher porosity, which is what you want, because in the filter, it's the pores that do the work for you, right? The pores are where you can tuck particles and have them removed, and it's the pores where the water flows through. So you want high porosity, so that means you would like a low uniformity coefficient, so it's close to 1. Here's a head loss equation, and actually there's two head loss equations that are commonly used. This is the Kármán-Kozény. It's the simpler of the two equations. I'm going to have you play with the ergon equation for the design challenge that I have coming up for you. The ergon equation is also in the textbook, and I didn't bother putting it here. You'll recognize all the terms in the equation. They're similar kinds of terms. The phi there, the phi filter sand is the porosity, and HL is a head loss, etc. What I want to point out, maybe of interest from a theoretical basis, is remember a long time ago, we talked about the Hagen-Poiseuille equation. Hagen-Poiseuille is the equation that describes head loss through a long straight pipe under conditions of laminar flow. And I have it there in the upper right. And just compare the Kármán-Kozény equation and the Hagen-Poiseuille equation, and you'll see that a lot of the terms show up like exactly or almost the same. So the head loss term is the same, the length of the flow path, L, or the height of the sand column that it's flowing through, that's the same. There's some funky coefficients out front that are different, but don't worry about those. What we're interested in are the big parameters that have units on them. The porosity, of course, we don't deal with that when we're talking about the pipe, but kinematic viscosity shows up exactly the same. The velocity shows up the same in both equations to the first power. There is this definition of approach velocity that's used in filters, and I think I mentioned this. The approach velocity is the velocity that the water would have if there weren't any sand there. Or if you have a downflow filter, it's the velocity of the water above the sand as it's going down before it enters into the sand. And I think we did this last week where we looked at once the water enters the sand, now you know the water speeds up, right? Once the water enters the sand, it speeds up because it has a smaller cross-sectional area that it's flowing through, the pores. And so it has to speed up to maintain conservation of mass. So in this equation for Kármán-Kozény, that velocity is not the velocity inside the pore, it's the velocity if the sand weren't there. And okay, D shows up exactly the same way and G shows up. So happily, both equations are dimensionally consistent and very, very similar. Okay. Now some fun with math. I don't know. Let's see. Fluids. How about statics? We're going to use statics to explain what the water pressure needs to be at the bottom of a filter in order to force that filter to begin to fluidize. Because fluidization is about a force balance. It's about there being enough pressure on the bottom of the filter to hold up all the water and all the sand that's on top of it. And if once that pressure meets that value, it will fluidize the sand. So we'll begin with, I should have put a point down here. Think about a point that is at on the very bottom of this apparatus, the very, very bottom, this dark line. There, think of a point down there. And we're going to figure out what the pressure is at that point, first by working our way from the atmosphere down to that point through the sand bed. And then second, by going down through this manometer. And maybe what's not clear here is somewhere there's some water entering underneath this filter that is pushing water up through the filter. So water is flowing, but we can still use this statics argument to figure out what the pressure must be at the bottom of the filter. So let's add up the weight of everything that's inside the filter box. So that's what this first equation is. So we're going to take the density of water and G, gravity, and we're going to multiply it by the height of water 1. So HW1 is the height of water that was above the original sand bed. And also HW2, which is the depth of water that was below the sand bed. That sand is just magically held up by something, some sort of underdrain system that doesn't let the sand leak down through, or an infinitely thin layer of gravel. That might break your brain thinking about an infinitely thin layer of gravel. So an underdrain system that doesn't let the sand down through. So those first two terms are the weight per unit area of the water that's above the sand and below the sand. We have to also add the water that's in the sand bed, and we know that the amount of water that's in the sand bed is the height of the sand bed times the porosity. So phi times the height of the sand bed is going to give us the equivalent height of water that is filling up that sand bed. And then we have to add the weight of the sand itself. So now we take the density of the sand times G, and the equivalent height of sand with no pores is 1 minus the porosity. So 0.6 times the height of the sand gives us the height of the sand, if you could just like consolidate it into one solid chunk of silica. And so that gives us the pressure at the bottom of the sand column. And then we have to do the same analysis going up through the water column. And when we do that, we get this second equation, rho manometer is equal to rho water times G. And then we have to add up all the heights in the manometer column. We have H1 and HW1 and HW2, just like we did before. We also have the height of sand. There's no water in there. I mean, sorry, there's no sand in there now. That's just water. And then we have this new unknown term, which is the actual head loss that is happening as the water is flowing through this sand column. And that's a height that we're going to end up solving for. So those two equations for the pressure at the bottom of the sand bed, they must both be true. We can set them equal to each other, and we can solve for our unknown, the head loss through the sand bed when we're backwashing it and it's fluidized. And we get this lovely simple equation that says that it's proportional to the height of the filter sand, which makes sense. And then there's these two terms, one minus the porosity of the sand and the density of the sand divided by the density of water minus one. And then this crazy thing happens. And I want to make sure that you catch this, that this crazy thing that happens is not something that is a universal truth. It's true with a particular kind of sand that has a particular porosity. And that is, if you have silica sand with a density of 2650 kilograms per meter cubed and a porosity of 0.4, when you plug those two numbers into the second two terms in that equation, one minus the porosity and times the density of sand over density of water minus one, you get 0.99, which is pretty darn close to one. Whew, take a deep breath. This means that when you fluidize a sand bed, the head loss through the sand bed is equal to the height of the sand before you fluidized it. Or watch this little animation. Or that is true, that the height of the original sand before you began to fluidize it is equal to the difference in the water level between what's in the manometer measuring the pressure at the bottom of the filter and the water at the top of the filter. I'm curious, does somebody want to ask a question? Because these are just crazy results. Don't be shy. Say, Monroe, this makes no sense at all. Okay, well, let's change this. Supposing we use garnet, and garnet has a density, I forget what, I think it's closer to 4,000 kilograms per meter cubed. What would you get in the case of garnet that is so much more dense? What would you find out about the head loss through that bed required to fluidize it? Do I still multiply by 1? As in, if it's garnet, we can say the porosity is still the same, but the difference is that the density of sand, density of garnet is a whole lot greater. So that rho sand over rho water minus 1 is going to be a much bigger number. And that means that the head loss is going to be a much bigger number too. So if you're trying to fluidize garnet, it's going to require a whole lot more head. And so, like, here's one very simple practical result. Our stacked rapid sand filters are very carefully designed, and they're designed for using silica sand. And if you, as a very clever engineer, said, I think it'd be more fun to use garnet in those crazy stacked rapid sand filters, and you replace the sand and took out the silica sand and put garnet in it, and then you tried to backwash it, it would be a complete fail. The filter hydraulics aren't capable of delivering enough pressure to backwash garnet. Anybody want to ask a question? So here's another insight from this analysis. So what actually happens at the moment of fluidization? Like, at one moment, the sand bed is solid, you can stand on it, it's there. And then a little bit later, it's all like a liquid, it's fluid, you can move your fingers through it easily. But what happens in the transition? And this transition, I feel like is worth some more research, because some funny things must happen, especially once you think about the fact that ultimately there's dirt in the filter. And so there's actually head loss as water is trying to flow through the pores of the filter as you're trying to fluidize it. And my best guess is that when you start pushing water quickly up through sand, at the very first instant in time, what happens is the entire bed lifts a tiny bit. And once it lifts a tiny bit, then the bottom of the bed can fall and can free fall, and then the fluidization begins progressively up through the bed. That's my bet as to what happens. And it started with that initially you had to actually lift the bed a tiny bit. And that matters because that means that in our filter system where we have lots of pipes in the bed, initially you're going to put a lot of force on all those pipes because you're trying to lift that whole sand bed, and the pipes that are in the bed are trying not to move. And so you'll apply a lot of force to those pipes right at that transition. And we have demonstrated this. We have broken things inside of filters because of not realizing how strong that force was. And then another one, sand will stratify if there's even a small range of sizes. So let's look at that in the next slide, I think. No, one of the next slides. We'll come back to that. So it's important that all the sand be close to the same size. We can also do one more calculation with this, where we have Carmen-Kozeny equation giving us the head loss as a function of velocity, the approach velocity. And we have this equation that gives us the head loss that you must have in order to fluidize the sand bed. And you can set those two head losses equal. And you can solve for at what velocity do you get just enough head loss to fluidize the sand bed. And that's a nice equation because it gets you the minimum fluidization velocity. And in order to fluidize a sand bed, you have to be applying at least that much flow. More than that, if you want to actually get that bed to expand a little bit and be a little more vigorous in its mixing. So this last equation, I show that there's an effect of kinematic viscosity, and you're saying that means there's an effect of temperature. So what does that mean? What happens to the minimum fluidization velocity if it is really hot and the water temperature is high? Then the viscosity is smaller, and that means I have to increase the fluidization velocity. Or sorry, the fluidization velocity increases. So in order to fluidize it, I have to push more water through that filter. So that means if you're designing a filter, you better design it so that it fluidizes really well, even when the water is warm. The diameter I'm focusing on there is what happens if there's different diameters of sand grains in your bed. What will that do to the fluidization velocity? And what's clear is it's a really strong effect. If you would double the sand grain size, it would multiply by 4 the fluidization velocity. So that's another reason why having uniform sand grain sizes in a filter bed is really, really important. I used to always go to the front of the class and draw this on the board, and I realized, oh, I'm not going to have a blackboard today. So this is a graph showing, and I forgot to animate it, darn. This is what happens as a function of velocity up through a sand bed. So there's the sand bed hanging out there on the right, and we're slowly going to increase the flow of water up through that sand bed. And we're going to measure the head loss, the pressure drop that's happening across that sand bed, and we're going to plot it. So under conditions of zero flow, if there's zero flow, there's no head loss. And so head loss starts out at 0. And then as we increase velocity, the Kármán-Kozsány equation applies, and we're just increasing the filtration velocity. And the Kármán-Kozsány equation says that the head loss is going to be proportional to the velocity. So we get this straight line. And then we get to the place where the head loss is equal to the depth of sand. And at that moment, assuming that it's silica sand, it completely changes. Now, the sand bed fluidizes, and from that point on, it doesn't matter how much water we push up through the sand bed, the head loss is the same. Now, I just said something which seemed a little bit bold. I just said that it doesn't matter how much we increase the flow rate up through the sand, it'll always have that same head loss. And you learned from me that you should always think about extreme positions and see what happens. So do you think my statement was right? If you just keep on increasing the velocity of water going up through, you get this tank, it's got sand in it, you're pushing water up through that sand faster and faster. And I'm saying that it won't change the head loss because it's always a force balance of that you have to be suspending all that sand. But what happens eventually if you keep on increasing the velocity of water up through that sand? Anyone, be bold. But can you think of something else that changes if I keep on going faster? Like, in your mind, did you send the water up through that sand really, 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 really fast? Like, what happened in your mind? What did you see? What did you see coming out of the top of the tank? You've done the experiment in your head, right? Anybody see sand coming out of the top of the tank? Yeah, because at some point, the velocity of the water exceeds the terminal velocity of the sand. And so the sand is going to go out. So this plot is missing another stage where eventually that black line has to come back down because there's no longer any sand in your tank. But there is this region where it's fluidized and it's expanding a little bit, but it's not coming out of your tank yet. And at that point, the head loss is constant. Over that range, it's constant. Anybody have a question about that? Because this plot is, I feel like it's a mind-blowing plot because I've always understood that head loss increases with flow rate, right? And now I'm showing you a plot where there is a section in the plot where the head loss doesn't change, flowing through porous media as a function of flow rate because it's fluidized. I feel like we already did this effectively. This is about the fact that we've got sand grains that vary by a factor of 2 in diameter. And if the sand grains vary by a factor of 2, then the fluidization velocity varies by a factor of 4. So we'd like to have more uniform sand. And maybe I will just present kind of the nature of the problem now that we're trying to solve. So I've given you some background on what's going on inside filters, concept of porosity, minimum fluidization velocity, head loss through clean sand. And now we have this problem that we could use slow sand filters, but I previously made the case that slow sand are interesting, but they're big because they're slow. And because they're big, they're capital intensive. And because they don't have any way of automating or mechanizing the cleaning process, it means that they're going to be cleaned by hand. Although granted, in London, where they have 80 hectares of slow sand filter beds, imagine the market value of that land, 80 hectares of land in London that is tied up in slow sand filters. And when they clean their slow sand filters, they have made very light, big tire carts that motorized carts that can go out and scoop off the sand and carry it off the sand bed. But in general, you'd be doing it by shoveling. So we're not so keen on slow sand filters. And rapid sand filters are cool. They're so much smaller, so they're going to be cheaper to make, but they require pumps to backwash because we need a lot of water going up through that sand bed in order to fluidize it and wash the dirt out. So we have neither of these options is good. There is a group that has invented a nice alternative, and it could be that this has happened on multiple places on the planet, but CEPIS is one of the groups out of Peru in the 60s, I believe, had a very nice system, and I'll show it to you, of a set of 6 filters that work in parallel and then work together to backwash one of the filters without using pumps. But this is definitely a call for invention. So this is the CEPIS system. There's 6 filters in a set. You can see the 6 filters there. And they have those 6 filters working together. And when they want to backwash one of them, they actually take the water from 5 of them that are still filtering water, and they use the water from those 5 to provide water to backwash the 6th filter. And they're able to do that without using any pumps. The dilemma is, in any case, backwash water has to be clean water. It takes a lot of it, and a lot of it fast, because the backwash velocity is high. And so these are the 3 choices. We could pump it from a clear well. That's what's done in most water treatment plants. The set of 6 filters working together, or we could have filtered water stored at an adequate elevation. So we could pump it, and that's what's done most places. If you pump it, then you also need to have a reliable electricity source, which means in most places that would mean you have to add a generator, and now you have to maintain that generator and keep it operational as well. And in many parts of the world, electricity is sufficiently intermittent that this becomes a real maintenance issue. Here are those 6 filters working together. I don't want to go into this in great detail, but you can see in the bottom, in this schematic here, that 5 filters have water going down through them. And there's the water on the bottom of those filters is all connected together. And so the water underneath them is shared and is going over to the 6th filter. And in the 6th filter, they opened up a valve that allows it to dump its water off of this trough. And so the water level in that filter drops to that trough. And now there's enough elevation difference between the filters that are filtering and the filter that is being backwashed. There's enough elevation difference to do 2 things. That elevation difference has to be enough to push the water through the filters that are filtering, and push all that water through the one filter that is being backwashed. And so this height here has to be the head loss in through the beds that are working to filter, plus the head loss required to backwash a filter. So that's a nice system. And then there's this question, well, what happens if you try to do this for a small community? And I do the math here, but the big concept is I've got 6 filters. And in order to backwash them, I need 5 of those filters to be getting enough water to then backwash the 6th one. And what if I'm in a drought and the water supply for my town is cut by 50%? What happens? And it turns out normal backwash velocities are on the order of double a fluidization velocity, which means that if you're at half the flow, you might not even fluidize the bed at all, which means you have no ability to backwash at all. So if you were going to build this system of 6 filters working together for a small community, and you learn that this community has low flow periods where they have less than 50% of the design flow for your plant available during summer droughts, what would you do? You see the problem? If we design one set of 6, come drought, we won't even be able to operate those filters because we won't be able to clean them. So what do you do instead? Yeah, Ravi's got it. You're going to design 2 sets of 6. And now you can operate at half the flow rate and you can still backwash your filters. So we just came up with this uncomfortable conclusion. I don't know if you felt the uncomfort or not, the discomfort. But operating with one set of 6 is very risky because you can't handle periods of low flow. And to solve that, you have to like double the number of filters. And so now all of a sudden for a small community, the minimum number of filters that you can use, you could easily argue is 12 filters. And when you propose that to a small community that you're going to build 12 filters to solve their problem, and each of those filters has valves and each of them is a little concrete box, all of a sudden you're beginning to look like a crazy engineer. So that's where I'm going to leave it as, oh my goodness, there are no good solutions. We're left with either we buy a generator and a bunch of pumps, or we have a crazy number of filters. Anybody want to jump in with a question or announcements? Okay, then I think you all got some feedback from Claire for your assignment, and Claire and I will come visit you in Gather. So see you in Gather. Bye now.